Actually, one thing before we get to this, well, I'll put it here, but I don't remember if we taught this or not, but what a salt is for a chemist. So if a chemist says a salt, it's a name for really most every ionic compound in chemistry. So, you know, we know through common experience a few salts. Yeah.
So like when you're like table salt, are they talking about just basic compounds?
Right. So if you say table salt, then you are referring to one kind. So if you use table in front, then you're referring to sodium chloride. Now, table salt usually is not just sodium chloride, it's usually potassium iodide as well. And if you, something wrong back there? Vibrating. What, the window's vibrating?
You see a grab truck and then like they heard
So sodium chloride is what we call table salt. Now you might also, have you heard of new salt before? That's potassium chloride. Wait, what now? Well, basically these chemicals right here. So potassium chloride is a new salt compared to sodium chloride and table salt. So sodium gives the salt the flavor that we're familiar with. Potassium chloride is a bitter taste, and so you use less of the new salt, and it's not usually as flavorful. It's more of a bitter taste. People use new salt to lower their sodium levels, though. So if they want to cut down sodium levels, then they will use new salt and replace table salt. But table salt usually also contains some iodide. Usually they add some potassium iodide to table salt too, because iodine is important for your thyroid functioning. And not so much here, but other countries have iodine deficiencies where the thyroid gland gets really big and it looks like a beach ball in your, well, maybe not that big, but more like a basketball in your throat. And it's just, but it's not common over here because we get iodine in our salt. Sometimes it can be really big. I mean, it can be, you know, or more like a grapefruit. It depends on the size of the person, but it can get pretty big. It can. It can get really big. You can. I mean, it's definitely possible that you can do that. Yeah, it's serious. It can kill you. So, what happens when? How do you get it? Without iodine in your body, your thyroid gland makes too much thyroid hormone. It just builds up in your body, and your thyroid gland gets really big, like a balloon. And yeah, it's really serious. But over here, we don't get that because we have iodine. Can you read that, Maddie?
not really, but it's kind of the change in where I go.
Oh.
Yeah, I just wear my glasses when I'm like random bored or driving.
I would be actually
Yeah, new salt. So that's how they, you know, it's just NU salt. So those are a few kinds. Now there's also others like magnesium sulfate, which is Epsom salt. So those are some of them that you might use in everyday life. If it ices, they put salt on the sidewalks. They usually use calcium chloride to do that. Because when you put this salt on the ice heats up and it melts. Regular salt can work too. It doesn't work as well as calcium chloride, but any kind of salt would help melt the ice on a sidewalk. but there's certain kinds that work better than others. So these are just a few, but what they have in common is they're all ionic compounds. They all have a metal with a non-metal present. They all look like granular substances, so they're going to be hard and brittle. They're going to have tiny crystals to make them up. They're not always white. You know, usually think of salt as just a white powder, but there's also pink salt, black salt, blue salt. Really, any color you can think of, you can find salt that color. Most of it's not edible. I mean, there's some pink salt that is edible. You might have seen that before, but in the Himalayas, yeah. But most of the salts that are edible are usually just white salt. But that's, for a chemist, that's what they mean when they say salt, not just things that are edible, but any ionic compound. Okay, metallic bonding. So metals bond differently than non-metals do. In the metal, what you have is the nucleus, which we'll just write like this. So this ball with a positive sign in it is just a positively charged nucleus. Now, in non-metals, what happens is you have electrons that are around each individual nuclei. That's how non-metals bond. But for metals, it's not the case. For metals, they're not confined to one nuclei or to one nucleus. The electrons just go all over the place. So you have the sea of electrons, and it's not orbiting one nucleus, it's just all over. So that's called the electron sea model, where electrons are not bound to one place, they move and they flow throughout the entire metal. And that describes how atoms that are metallic bond together. Electrons are not bound to a nucleus, but flow through the entire metal substance. Those are the electrons. Oh, yeah, that's a good question. Yes. So I didn't say this, but yes, they're only valence electrons. What's wrong with there, guys? Well, it's just the truck. It's going back and forth. That truck is making it vibrate. You hear the garbage truck out there? Like when it vibrates, it makes the road vibrate. Wait, what? Yeah, it's just making the windows vibrate like that. So back to that question. So yeah, so that's a really good question to bring up about the valence electrons. So there are core electrons. We didn't really get to this, but the core electrons do stay bound around the nucleus. So these are just valence electrons that are flowing around. So the valence electrons are the ones that move through the metal, and the core electrons do stay around the nucleus of each atom. Well, they behave in different ways because the core electrons don't participate in bonding, so they don't bond with their atoms. Core electrons just stay by a nucleus and really don't do anything. For a chemist, they don't really help the chemist know what it's going to do. Only valence electrons move around and they bond. Because the nucleus is able to keep them there because they're closer to the nucleus. The nucleus is more powerful for those ones. It can pull them in, but the valence electrons are too far away. They can't hold on to those very tightly, and so they're freer to move around. So electrons, and yeah, this really, as Marina pointed out, valence electrons are really what we're talking about here. are not bound to one nucleus, but move through the entire metal. And because that happens, this describes metal's properties. Because electricity, what is electricity made out of? What is the substance of electricity? What kind of particles are in electricity? Very good, exactly right. It's electrons. That's what electricity, it's just electrons in motion. So if you have electricity when you have electrons in motion, but what do you have in metal? Well, you have electrons in motion in metal. So that's why metals can move electricity through, because electricity is just electrons in motion, and metal is the same exact thing. It's also electrons flowing through. So that explains why metals are conductive and why nonmetals are not, because nonmetals, just write this over here on the side just so we understand the difference between the two. If you were to look at a nonmetal, what you would see is just the electrons only staying around one nucleus, just like that. You're not going to see them flowing through. And so electrons can't flow in a nonmetal, they stay in one nucleus. So nonmetals, like wood, for example, are not conductive. Electrons can't move through those things, but they can move through metal. Yeah, they just flow through, that's right. If it's a nonmetal, they just stay around one nucleus. Yeah, that's called, usually that'd be covalent bonding or ionic bonding. So nonmetals could bond through two things, either covalent bonding, which we'll get to later, or ionic. So in both of those kinds of bonds, there's three kinds of bonds: metallic, covalent, ionic. And metallic bonding, electrons flow through, and covalent and ionic, they don't. They just stay in one place, in one atom. So this also explains why metal is malleable. Did we talk before about what malleable means? Do you remember what that means? Very good, exactly right. Yeah, to be hammered into sheets. So if you can hammer something and it becomes flatter, it's malleable. So metal is that way. You can make metal into a very thin sheet. Why does it happen? Well, when you push against the atoms, they don't break apart because the electrons are flowing through the entire thing. So it's like silly putty kind of, where the atoms can just move around and they're more flexible. So metal is bendable, it's flexible, it's not as easily broken because the atoms don't break apart. In a nonmetal, each atom is separate, and so it's very easy to break apart that bond between these two atoms. When you do that, you tear it or you cut it. But for metals, what you have instead is no really clear boundary between where each atom ends. You have just the sea of electrons that moves through. So when you apply pressure to the metal, what happens? Well, this nucleus right here can just move around. It might move around here, but you haven't broken apart the nucleus off the metal. To make the metal break or tear, you have to cut off one of the atoms from the rest. But it's hard to do that when you don't have a clear boundary for each atom. Over here, you can very clearly see where each atom begins and ends. Over here, it's not as easily apparent where the boundaries are. And so you can move around these atoms a lot more easily. And that's what you see when you bend metal or when you crush metal, when you hammer metal. You're just moving electrons around with the nucleus, but you're not breaking off the atoms from the metal piece. So it explains why metal is malleable, why it's bendable, flexible. Of course, every metal is different as far as its flexibility goes. Some are more brittle than others, but metal as a whole is bendable and flexible. Yeah. That's right. Exactly. Also explains why it's ductile. What does ductile mean? Did we go through that one? To make it into a wire. So ductile means to be able to be made into a wire. Metal is durable. So you can hit it and it stays intact. It doesn't shatter. Metal is not easily broken. It conducts heat and electricity. And that's again due to the electrons moving through that it can do those two things. And then it's shiny. And it's shiny due to the electrons bouncing off the metal piece. So electrons can absorb and release photons, and they can either have electrons bounce off or have the photons bounce off. And that gives you a shiny, like the shiny feeling that you see with metals. So it's the movement of electrons and photons that creates a shiny thing shiny luster you see in metals. So electrons are what create color and what create light and different things. And so you have photons bouncing off, electrons bouncing off. You have different colors that you see along with different lights you see. The other thing that goes through is boiling point. So metals have high boiling points. They're usually at room temperature, they're usually solid. There's only one that's not. Mercury is liquid at room temperature, but everything else is solid at room temperature. So for iron, its boiling point is 5,184 degrees Fahrenheit. Yeah, these are metals, yes. So that's the boiling point. And then the melting point for iron is a lot lower, about 2,800 degrees Fahrenheit. So metals have a moderate melting point and a very high boiling point. So it doesn't take extreme energy to make atoms move past each other. They can flow through, but it's very hard to get atoms to leave into a gaseous state. So melting point, we can achieve that fairly easily. We can melt iron, other metals fairly easily, but it's very hard to get a gaseous metal. And so boiling point is really extreme for metals because it's so attracted to the nucleus. The electrons in the nucleus have a very strong bond with each other. It's not that hard to get atoms to flow through metal and make it melt, but it's very hard to make them get off from each other and fly out into the air with a boiling point. There are a few metal alloys that we talk about too. So an alloy is a mixture of two or more elements. And you have sterling silver is one common alloy. So it's 92.5% silver. And it's 7.5% copper. Another one is steel, which is made of iron and carbon. And the amounts vary based on the kind of steel you're talking about, but there is some mixture of iron and carbon. The carbon makes the iron stronger, it keeps it from rusting. And you have ones like bronze, which is a mixture of copper and tin. And you have brass, which is a mixture of copper and zinc. So they melt the two metals together, combine them, and then when it goes back to become hardened, then you have an alloy of two metals. Generally, it's done to make it either cheaper, like sterling silver. It's a little bit cheaper to do it this way. Keep it from tarnishing and rusting, make it stronger too. Okay, so we finished chapter 7. Today, I want you to, you happy to finish chapter 7? But are you clapping your hands happy to finish chapter 7? It was, yeah. So, have a what boiling point? They, well, not that high, but all metals as a whole do have high boiling points.
Are they all like extreme and then moderate for their boiling?
Right, so they're usually moderate melting points, extreme boiling points. That's a standard characteristic of metals. So others have, it can be 4,000 degrees, 3,000 degrees to boil, but they're all very high boiling points compared to their melting points. Okay, I want you today to work on questions on page, let's see what page it's on actually. End of 7.4 on page 228. Do 40 through 45, but skip 43. And then tomorrow we'll do the chapter review. I'll write on the board the questions you need to do for the chapter review tomorrow and on Wednesday. The test on Thursday this week. Well, 43, I don't, 43 you can skip, but 44 you can do that one.